We have 3 talks scheduled, and our first one is by Alex Himonas from the University of Notre Dame. So thank you, Alex, for agreeing to give a talk. And he's going to be talking about initial boundary value problems for dispersive PDEs. So thank you very much, Alex. Take it away.
Oh, well, thank you very much. Thank you, the organizers, for giving me the opportunity to talk about my work with collaborators. I am right now in my office at Notre Dame, 90 miles east of Chicago, close to Michigan Lake. Weather is rainy, otherwise everything is fine. So let's see the abstract here. This is work with collaborators, Athanassios Fokas, DionyssisMantzavinos and Fangchi Yan. We are going to talk about well-posedness of initial boundary value problems for an LS and KDV. And we are going to use for this the unified transform method. We will discuss this later. And we will do the KDV, which is one-dimensional, the 1D NLS, and 2D NLS. So before, since we are going to be talking about well-posedness, recalling that this is an important property for a PDE problem with supplemented with appropriate initial boundary conditions, and consists of existence, uniqueness, and stability. So if these 3 properties hold, the problem is well posed, otherwise it's called ill posed. And as we saw in the other talks, that well posedness is very important for PDEs modeling physical situations. Let's be a little bit more specific. And in this talk, we're going to use the data space will be the Sobolev space. And here in 1, we define the Sobolev space is a weighted L2 space. And trying also to be a little bit more specific for the properties, having in mind the KDV and the NLS. The existence consists of having initial data U0 in HS. We can find a time and a solution in the space of functions that are continuous in time, and Sobolev in X, solution to KDV or NLS. And this, we call this the Hadamard space. And this solution is unique in this the Hadamard space. This is the second property. And the third property is the data to solution map is continuous. This is the basic stability requirement of Hadamard. In other words, if we have initial data UN0 going to infinity 0 in HS, then the corresponding solutions UN that exist in the space of continuous functions from the time interval to Sobolev spaces converge in so-called Hadamard norm, and here is the condition here down there. And here is Hadamard. And let's recall the well-posedness for the initial value problem. If we want to study the well-posedness for the KDV initial value problems, we do this in 3 steps. In the first step, we replace here is our KDV, the nonlinearity. We replace the nonlinearity with the forcing, and then using the Fourier transform, we turn the PDE into an ODE, and then solving this ODE, we produce the solution formula. The solution formula that is we see here is in 7. And the second step is to derive linear estimates. The linear estimates here for data in Sobolev spaces, and for the forcing to be in the Hadamard here, no, in the Bourgain spaces. So, and after some hard work, one gets, not really too hard, gets the first linear estimates. We have the solution multiplied, the solution multiplied by a cutoff, estimated in Bourgain spaces is bounded by the Sobolev norm of the data plus the Bourgain B minus 1 norm of the forcing. These are the linear estimates. And then we go to the solution map, replace the forcing, the solution map replacing the forcing with the nonlinearity, and we produce the iteration map. Here is the nonlinearity. And then this is proven the bilinear estimates. This is a difficult, estimate, proven the bilinear estimates 12. And we are able to do that for the nonlinearity in Bourgain spaces if S is bigger than minus 3/4. And for the parameter B in 1/2 1. Then using this, one proves local well posedness for the KDV if S is bigger than minus 3/4. In fact, to have a solution is unique in the Bourgain spaces, and the data to solution map is better than Hadamard requires. Is ellipse is continuous instead of just continuous. Okay, let's recall now for the NLS. The NLS, we have seen this equation in many talks in this conference. Here we choose the cubic NLS, and again, we solve the linear problem with forcing, and again, using Fourier transform, we get the solution map here, the solution here, in terms of the data. The data here is supposed to be U0, not phi, and the forcing. This is the very easy step. This is undergraduate calculus. And then using, we produce the linear estimates with data in Sobolev spaces and with forcing now in the Hadamard space, not in Bourgain spaces. This is an easier space. And here we produce the linear estimates for the NLS. We have the solution of the forced linear Schrodinger with data U0 and forcing F in the Hadamard norm. It's bounded by the norm of the data and the Hadamard norm of the forcing. And now, again, the same story repeated for the third time. We replace the forcing with the nonlinearity, and we have the iteration map. And using the algebra property to take care of the nonlinearity here, the algebra property here holds for S bigger than 1/2, then we are able to prove this local well posedness result for NLS, but for S bigger than 1/2, for smooth data, continuous or better. And if we want to get S greater or equal to 0, then we have to use Bourgain spaces, and the proof becomes much more delicate. So this is the story of the initial value problem. There is lots of work here. The modern theory begins with Bourgain in 93 that gave us the Bourgain spaces to get the best analytic results. Continues with other results in this direction we have with Kenning, Ponce, Vega 96. For the KDV, go all the ways to minus 3/4. And then we have more results by Colliander, Kiel, Staffiliani, and Tao, and many others that are not listed here. And Before this, we have another work with Kenning, Ponce, Wenger that they went to 3/4, down to 3/4 from the earlier result of Bonner, Smith, and more authors that they proved up to 3/2. This is a short mention of the results for the initial value problem. For the KDV and for the NLS, we have results in Bourgain spaces by Tsutsumi and more classical setting, Kazanave, Wiesler, Kenning, Ponce, Wenger, and many others. So here we're going to talk today mostly about the KDV initial boundary value problem. And here again, we have the work by Colliander and Kenning for the generalized KDV, Bona and collaborators, Holmer for KDV, and for the NLS again, Holmer, Bona and collaborators in 1 dimension, and then we have also in 2D by Ran, Shun, and Zhang, and Ondierd. So for studying the initial boundary value problem for NLS and KDV, there are 3 approaches. The first is the one based on Laplace transform in time, which is implemented by Bona and collaborators. Then we have the one that expresses the initial boundary value problem via initial value problems. And this is Colliander, Kenning, and Holmer. And what I'm going to focus today is the unified transform method approach, which is I'm going to talk about, which is in analogy to the IVP that we saw earlier. I'm sorry, there is lots of information here, but that's the way things are. So we are going to demonstrate this method for the NLS, for the cubic NLS. Here, the initial data are in Sobolev spaces on the half line, and the boundary data, Dirichlet data, are in H 2s plus 1 over 4 in an interval 0t. This is the time regularity, known time regularity for the NLS. And here what we are going to do, we are going to follow the approach of IVP. We are going to solve the linear problem. We are going to derive linear estimates, and then we are going to replace the forcing by the nonlinearity, and we are going to try to prove contraction in some appropriate space. So just to remind you, if you have seen this method, if you have never seen it, I have provided a few more details here. Here is the forcing linear Schrodinger IBVP. Here is the forcing. So if we use these exponential solutions, these familiar exponential solutions that are solutions to the adjoined problem, homogeneous linear Schrodinger equation, then after some manipulation, we convert the PDE here, the linear Schrodinger equation with forcing to divergence form 26. So here seems to be first order, but it's not, because there is another derivative here for u. But in any case, after using integrated 26 first with respect to x over 0 infinity, and then t over 0t, immediately gives rise to the Fourier transform over the half line, this Fourier transform over the half line, and some time transforms here for the boundary data, the given boundary data here, the Dirichlet, and the unknown boundary data here that we don't have it, and we derive this global relationship. The global relation, it is everything is here, and taken now, seeing this global relation, getting the inverse Fourier transform, we produce the solution. Unfortunately, the solution here via the inverse Fourier transform, the formula involves, in addition to the known Dirichlet data, transform of the Dirichlet data, and the forcing, it involves also the Neumann data that we don't know here. And the method, what it does a certain trick in order to remove the Neumann data. We do that by getting the term we have here, this term. We get this term and using analyticity here, using the analyticity property of the half-line Fourier transform, we deform the integration for going like this. We deform the integration into this domain. So if we do this deformation, then we obtain this formula. The previous formula that we had before, we have it now. Here, instead of having integration over R, we have integration over this interesting domain. In the domain that allows us to remove the data. And we remove this Neumann data because we notice the symmetry here. We can replace K2 minus K in the global relation. And of course, I should have mentioned in the half-line Fourier transform, the important thing, the half-line Fourier transform is analytic, well-defined on the upper half plane. So then we solve this global relationship now for G1 and replacing now up here the solved relation here, we get the so-called the Fokas solution formula, which is big. If you compare it from the initial value problem, we will have this that comes from the initial data, and we will have this that comes from the forcing. In the initial boundary value problem, we are going to get first we're going to get the extra term, which is from the boundary data, and then we're going to get two more terms, this one at minus k and this one at minus k, that comes from removing the Neumann data. And so this is the complicated, the more longer complicated formula, and this is the solution of the linear problem. So we have implemented the first step. And once we implement the first step, then the next step is to provide the linear estimates in analogy to the IVP. The linear estimates is the 32 here. What we do here, we are using again the Hadamard norm. The Hadamard norm, we estimate the solution in the Hadamard norm with the data and the forcing in this way. And then we produce the contraction, we replace the forcing with nonlinearity, and our objective here is using the algebra property again, we prove contraction. This is the method, and then we have the theorem here, which is we have a local well-posedness for the initial boundary value problem on the half line. And since we don't have much time, I'm sorry, I'm throwing at you so many symbols. Here it is, the long solution formula following the Fokas method for the KDV. So you can implement the same three steps method for the KDV. And here the domain D plus for removing unknown data and doing the estimates. It's very important. And here is a difficulty doing analysis, doing estimates on these rays in the complex domain, and you get well-posedness local well posedness. And here you have also for a higher dispersion KDV, you can implement this method for a higher dispersion KDV. The Fokas solution formula will be very complicated, but very beautiful. And the domain, the one domain will be replaced with more domains depending on the dispersion. And here is a local well posedness result. And I, at the end of my talk, I arrived where I want to talk the new result. The newer result, it's the 2D NLS. The 2D NLS and on the half plane. Here, again, we are following the IVP approach that we saw it for the IBVP in one dimension, space dimension. We solve the IBVP, produce the linear estimates, and we prove contraction. Here is the forcing problem, and here is the more complicated long formula, which looks complicated, but the derivation is straightforward. It's like the one-dimensional case. And here, in this formula is what you saw earlier. In addition, you have integration. The x1 variable is over the whole line. So here you have Fourier transform over the line for the x1 variable, half line Fourier transform over the second variable, and the magic domain D is this in the K2 variable. And here is the time transform. The interesting thing here is to discover what is the space of the boundary data. Once in order to do that, we assume the simplest possible situation. In other words, the forcing is 0, data are 0, and we get here the boundary data on the half plane, and we assume this boundary data to be as beautiful as we wish and support it in the half plane. If we do that and estimate the solution, this is the solution, the complicated, the long solution formula collapses into this simple one. And if we estimate this solution for fixed time in the Sobolev spaces of the half plane, immediately we see, not immediately, after some work, some interesting work here, Bourgain spaces arise. We bound the solution of this reduced IBVP problem from the Dirichlet data in these two norms, S1/4 and 0 to S plus 1/4. And here is the Bourgain norm that has two characterizations. And if we put these norms together, here we have the Hadamard norm of the solution to the reduced pure IBVP bounded by the Bourgain norm of the data. And now what we do here, we, in order to use this theorem, this nice theorem, in order to use it for the general data, for the general situation, we decompose the forced linear IBVP, as you see here, to two IVPs. One is with extended initial data, and the other is with extended forcing. And then two not reduced pure IBVPs, but two pure IBVPs. What here is missing the compact support. And here some work is required in order to apply the previous beautiful estimate. And if you do that, then and you use not the space BS, because the space BS is global, we restrict into the line in X1 and the interval 0t in time, and then the restricted Bourgain norm now takes this. We put the time part as a Sobolev time norm. Here is the B parameter, and then we have the linear estimate, and the linear estimate, it is again, we have the solution of the forced linear IVVP in Hadamard space when S is between 1 to 3/2 is bounded by the Sobolev norm of the initial data, the restricted Bourgain norm of the boundary data, and the Hadamard norm of the forcing. And of course, the last step is to do the here to replace the forcing with the nonlinearity. And if we do that, then we are going to obtain the theorem here, which if here is the smooth case, the data are smooth, and you have this compatibility condition, and then we for given initial data U0 and boundary data G0 in the appropriate spaces, then we get a solution in this space where the lifespan is given here by 46, and again here the data to solution map is better than continuous. In fact, this local ellipse is continuous. And with this, I would like to thank you. Any questions?
Fantastic. Thank you very much, Alex. A really nice talk. So if anyone has any questions, feel free to unmute yourself and ask Alex directly, or you can put it in the chat and I'll read it out to Alex. But while we're waiting for, oh yeah, go ahead.
I have some questions, that's okay.
Yeah, of course.
Thank you for a very nice talk. I had perhaps a technical question and a more general question. So for instance, in the 1D case for NLS, you had some restriction on the time t star on which the result was established. Is it for convenience, or is there an obstruction into having
well, here, this is the theorem.
Yeah.
Sorry. I'm going the wrong way, I'm sorry.
Yeah. What was it?
Let's get it.
No, it was before on the 1D case, but I guess.
Here. What is the restriction?
Yes, thank you. Yes, yes. So this restriction on having a fixed time interval, or I mean the fact that you start on, is it possible to consider a problem posed for capital T tending to infinity? Or?
Yeah, this is a local. This is local well-posedness.
Yeah.
It's not global. In fact, this is a very interesting question. We did not explore that. Of course, you expect to have, and there are results. I think there are results. Jerry, I think, has done the global with his method. Here, this is just local problem, local answer,
okay.
local well-posedness.
Okay. But so global is also for initial boundary value problem that's been established.
Yes. Yes.
Okay. And the other case is that in the other question, in all the results you presented, it seems that having integrability in the lax pair plays no role, because you could just do 1D.
Yeah, this is, all these things play a role when you go to global and study more fine properties of the problem. Here is just local. When you do local, you can you don't use these things.
I see. Yeah. Okay.
It's more harmonic analysis. Is more.
Yeah.
You're using, however, the nature of this kind of the Fokas method, the solving. It has been motivated by integrable equations.
Yes. Yeah. That's more the perspective I know.
And when he presents it, and you look at his book, it has this spin. Myself, the way I present it, I'm trying to do it as in the PDE language.
Yeah, in the PDE. Yeah. Okay, I get that. Okay, yeah. Thank you. Yeah.
Yeah.
Thank you.
Alex, I have a question.
Yes.
So look at the slide that you've got up right now.
Yeah.
Actually, in this slide, you don't impose a compatibility condition, which of course you need.
Yes. If I don't impose it, it's missing. It's somewhere lost.
Right. Exactly. Now, what I wanted to ask was, you say S bigger than a half, but actually, if you took large S, you would need further compatibility.
Well, Jerry, this is you try to give me a hard time. This is S bigger than
sorry,
1/2.
early in the morning.
No, S bigger than 1/2. I'm cheating here. If I have to give you proof for S bigger than 1/2, I have to do lots of things are missing. Actually, to tell here, it's better to say S between 1/2 and 3/2. What it is, Jerry?
Right. That's what you had for the 2D.
I try to be very honest. I apologize here. 1/2 smaller than S, more than 3/2, then everything is fine if I put the compatibility condition. Otherwise, I'm lying.
Well, no, otherwise you need more conditions and it becomes a real mess.
That will need more time too.
Right. Nice talk, Alex.
Thank you.
Yeah. So I'm probably going to have to call time on questions because it's time for our next talk. But Alex, I imagine you're around for the rest of the week if people wanted to ask you anything more.
Yes, I'm available. Thank you. I hope it didn't terrify people with all these symbols.
No, it's a very interesting problem. And it was a really nice talk. So thank you very much, Alex.
Bye.